We got really close in second period. Hey, if you have not done so, open up your hand. Oh, hush. That surprised me that who needs paper version? Because I always have them on camera. No. Who else needs paper version? You have a originally, I think I used I don't know. I originally had you in 9, which yes, is that one. Okay, then I will cross that back out. Okay, y'all. I need to be able to get through everything with y'all because first period was like a whole whopping 20 minutes long, so they weren't recording that. And then second period, we got like this close, and we ran out of time. Y'all, I spent a good solid week building this over the break. Where's my attendance paper? My goal was to have the entire 6 weeks done, and yeah, it didn't happen. But I built through this week and next week. At least I know what I'm doing for this 6 weeks. I see Billy. Get to the right class. Billy, Brady, Braden. I do not know who is in person and who is not at this point. I mean, everything's changing so much. Now, I can tell you, if you missed the 6 weeks exam, I just sent you an email during third period letting you know that it was open and where to go to find the information. Matthew, Avery, Billy, there's Christian, Camille, Brady, Avery. When you do take the 6 weeks exam, you have to go back to the module from right before the break. There's instructions how to do it. Please email me and tell me that you've taken it, because it's a totally different program than Canvas. It won't tell me. And if you don't tell me, then I can't put it into fixed grades. So who's missing now? We are picking up where we left off from before the break, because I know all of you studied plate tectonics over the break. Where's Bennett? Oh, you're back up. It's plugged in. It's the red one by those bottles. That's the one that's plugged in. Haley. Yeah, there you go. Yeah, I don't see Devin. Garrett. I don't see. If I'm calling you online, it's just because I haven't seen you. I haven't seen Garrett. Marissa. No. Jason. Oh, I see Marissa online. Jason. Brady. Oh, no, I see Brady online. Those of you that are ticking in.
Yeah, I'm here.
I got you.
I was just making sure.
I got you. Christian's here. Austin, Erica, Brady, no. Cooper, no. Colton, yes. Erica, okay. Kayla, no. Jared, no. Ashton, yes. Skylar. Okay, I will double check. Let me get up onto the right slide. Okay, y'all. Once again, y'all. Y'all, hush. We are picking up data. Y'all, Haley, we are picking up where we left off. Except for you. You can leave. We started plate tectonics right before the break. Because the second 6 weeks was only 5 weeks, We have to finish plate tectonics. Really should have been shoved into last semester, but there was no way for me to physically do all of plate tectonics in 2 days. Yes.
I saw a TikTok where it said that the inside of the earth is just, we don't even know what the inside of the
Yeah,
earth.
it's just all. Oh, I'm about to explain to you why do we know what we know? It's called technology and seismic waves. So. Oh, no, it's not. Okay, so since that is the opener, how do we, I just told you the answer, how do we actually see inside the earth? What are those machines called? You're right. You are so close. It's not what they're called. They're called seismographs. You are so close, though. I know what you meant. This is not what they were called. So basically what we do is we listen to the echoes of what?
The fighting against the inner and outer.
No.
What do we call them in regular English? No. What do we listen to?
Oh, the shaking.
The shaking. What is it called in English? What is the shaking called? Earthquakes. There we go. We listen to earthquakes. We listen to their echoes. We listen to their reflections. Y'all put your phones away. Can we dig into the core?
No.
No, why not? And we'd melt. Well, not really melt. We just sort of vaporize. So we'd be crushed to death as we're burning alive all simultaneously. Sounds really fun. But no, we can't dig to the core. We can't dig through the earth. There's no such thing as digging to China. So we the whatever you call them, I forget what you said. The private radiator or something like that is what you called it. We see by listening to echoes inside the earth. It translates. It's not necessarily sound. I don't know how many of you have had physics. We're about to find out how many of you can follow some of the language I'm about to use. But we talked about this individual before the break, Wegener. It's not pre-electricity, but 1912, you didn't live in the city, you didn't have a chance of electricity. He was the one that introduced what was called the hypothesis of continental drift, which, yes, I know is the name of an Ice Age movie. Actually, we watched through the break. But he didn't understand that there were 2 types of crust. He only thought that there was continental crust, hence continental drift. He didn't know that there was oceanic crust. They didn't know. It's not that he was stupid. They didn't know. They didn't have the technology. They didn't have the satellites that did topography. They didn't have seismographs. We didn't have any of the stuff that we have now. In fact, his colleagues thought he was a crackpot. Crackpot. He was crazy.
Yeah, but think about that. We're probably, because how.
When you talk about future technology, yes,
Yeah.
we're stupid. I almost said a bad word. I almost said the R word. We're stupid compared to the future.
Yeah. There's probably another concept.
Is stupid a bad word too nowadays? I apologize.
Oh,
Offend
are you
anybody.
insulting me?
No, I'm not insulting you. Just twist my words.
I cannot spell.
You can't spell.
Yeah.
Now, he had a lot of evidence. He had these fossils, which I'm really hoping my fossils come in for when we do that part in a few weeks. I still haven't gotten the stuff I've ordered. He had these index fossils where certain critters were alive at certain times, and therefore they were deposited in certain layers of sediment. And then we had this horizontality where certain layers are on the bottom are normally older, and the ones at the top are normally younger. The fact that the continents fit like a puzzle, okay, so he had that going for him. But he couldn't quite prove it. In fact, in 1930, he did an expedition to Greenland trying to prove this stuff, and he died because he was exposed to the elements and he froze to death. At least he died doing what he loved. Okay, so once again, we talked about this individual before the break. I just know you didn't study my class over the break. I don't blame you. And tectonics we only did 2 sections, and it's going to go through the next 2 weeks. So we're going to go into this in more depth, but modern technology, electricity, these things that everybody's addicted to. We have satellites that map the Earth. They give us different elevations, which we call topography. You will learn how to read a topographic map. If I had the supplies, we would build a topographic map, but I don't have that. They didn't have planes in 1912. Well, actually, I'm not 100% sure. I don't remember when the Black Brothers did the first flight, but we didn't have the ability to take photographs from the sky like we do now. No. They didn't understand the striping, the pole reversal on the bottom of the ocean floor. Every 500,000 years, magnetic north and south flip. Not the Earth turns upside down. But when you take a look at the iron on the ocean floor, they're reversed. The Earth has to do that or it can't protect itself from the sun and everything gets vaporized and dies. Well, at least on the surface. Down at the bottom of the ocean, there. That's the creation of life. That stuff's still pretty much golden. But everything up here on the surface, we die. We can't survive gamma radiation. It's not like it's sunburn, it's like melting flesh. Now, the other thing that we mentioned, before the break, was that these plates, which there are 12 major plates, you don't need to know their names or anything like that right now. There's a bunch of minor plates, but they sort of ride along the surface. And so that surface is called the asthenosphere. Now, obviously, the surface is the crust. That's what we want. David, put your phone away. But the asthenosphere is this, it's not liquid, and it's not like plastic like this, but it's this very slow moving, hot, solid goop. Just like that window is technically not a solid. Because you give that window enough time, a couple hundred years, and the bottom will be much thicker than the top, because that's a very, very slowly moving liquid. It's so slowly moving that if you hit it with a hammer, like if I don't know where I put my rock pick. So I'm not going to hit it. But if I hit it with my rock pick, it would shatter because it's that slowly moving that it acts like a solid moving. Just like the interior of the Earth. And once again, not this top part, but this part we covered before the break. Okay, so no, you can't dig through the Earth, you'll die. For multiple reasons, you will die. Okay, now up until 1989, the deepest we went was a Russian borehole, and I cannot remember the name of it. I have to look it back up. It took them over 20 years to dig that particular borehole or well or whatever you want to call what you dig down in the earth. But the deepest one, and I fact checked myself like crazy over the break. This is pronounced Qatar. That's how you pronounce this town. It's or not town, country. It's in the Middle East. Qatar is how it's pronounced, at least with the American pronunciation. I don't know about the Middle Eastern pronunciation. You're going, I don't know, divide that by 5,280. That's how many miles down they went. To my knowledge, this is the deepest that we've actually been able to dig. I can't remember if there's been more on here or not.
When you think like theory, wouldn't you be able to stop bombs in one area?
To do what?
Theoretically. I mean, the ash fire, you wouldn't be able to see the hole until like basically a very long time after. But would you theoretically be able to go and open up the area?
No.
No.
No. Now, theoretically, if you went to the center of the Earth, let's just pretend that we can survive magic. The magic tool bus time, right? So You go to the very, very center of the earth, and you have a lot of pocket, and you're trapped, and you can't ever leave. You would float too, but you would never leave.
How do we look inside the hole?
Seismic waves, earthquakes essentially, whether they be natural, being earthquakes or man-made.
Well, I mean, like in the crust. Theoretically, you'd be able to make a hole in the crust all the way to magma.
Yeah, but once you come in contact with magma, you're dead. You can't survive that. I mean, go swim in a volcano and see what happens. Don't really do that. I'm not like literally challenging you. I'm not, but we do know the diameter of the Earth, approximately 7,500 miles, and knowing the diameter of the Earth, and then measuring the differences of the two major types of seismic waves. The two major types of waves and how they bounce off of things, or how they bend as they travel through things, or possibly don't travel through certain types of substances. That's how we know how thick the interior layers of the Earth are. I don't know if this is the class that, I think it was you that asked. Somebody asked, well, how do we know that it's this thick or that thick? It has to do with the difference between the S and the P waves. Some of them only go through solids. Some of them go through solids and liquids. Some of them bend as they travel through certain materials at different speeds, for that matter. That's how we know where earthquakes start from. Have any of you all ever lived in California and had to deal with earthquakes? Probably not.
I'm moving there.
You're moving there? I would not want to live in California. But although it's beautiful, I will say that. Certain areas are beautiful. I've got family members that, Haley, I've got certain family members that live towards San Diego. Very, very beautiful, very expensive. 1,500 square foot house is worth over $1 million, just so you know, in California. Just throwing that, it's extremely expensive.
Yeah, but also minimum wages are low.
Exactly. So this is how you, Haley, this is how you spell seismic.
I know, I found
Okay,
it
all
on the
right, you
other
found it? All right. They're essentially earthquakes. Okay? Earthquake is the natural term. Now, I don't know if any of you are interested in paleontology. Used to be, we just had to dig and hopefully find dinosaur bones. Now, you blast the ground with seismic waves, and it shows you where the bones are.
That takes all the fun out of it.
Well, but that's what they do. The echo, okay, off the bone shows you where they actually exist. If it strikes and bounces back, like when you look at the mirror and your image bounces back into your eyeballs, that's called a reflection. I think your reflection is called a reflection. It bounces back.
And why doesn't vampire
Haley, vampires, if the wave hits something that has a different density, if it's more dense, and I don't know how many of you know your physics, but if it's more dense, it gets bent in to the normal, more up and down, like straight up and down. If it hits a material which is less dense, it bends away from the normal. For those of you that are fishermen, you know that that fish is not where it looks like it is. It's not. It's called Snell's Law. I could teach it to you. It's really not that hard. Just a tiny bit of geometry.
Is it the straw thing?
Yes, the straw thing. Yes. It has to do, are you going from a less dense to a more dense, or a more dense to a less dense, as to which direction it bends? But that is called refraction. With seismic waves, and this is a little different than physics, if it seems to disappear because it's been absorbed within the earth itself, that's called attenuation. That is a different phrase than what I'm used to. With physics, the other word is called diffraction, where it's if a wave goes through an opening, it spreads out, which is what makes a cone circular.
Isn't this all about like tiny rainbow thing?
Sort of. Now, the way that a rainbow is created is refraction of light.
Yeah.
Now, that's a single rainbow. A double rainbow is it's a reflection refraction. A triple rainbow is a reflection refraction.
Yeah.
I've never seen a triple rainbow in my life. I have seen double rainbows. They're extremely bright, like painful to look at, kind of bright. Uh-huh.
I've seen so many.
Normally preceding a really bad storm,
Oh.
but they're like bright. This, which I don't think you guys have on your paper at all, if they're very shallow, they give you great detail. If we're talking about a lot deeper, there's less detail. So this is and I don't know where this one, I just yanked this one off the internet, but you can see the different layers of the rock, which corresponds to their different densities. This is a reflection and refraction, not attenuation. Like I said, the deeper you go, the less detailed your images are going to become. Not that they don't matter, I'm not saying that, but the shallow ones give you the very, very specific info. I think I put this one on your canvas.
You did.
There are two major types of seismic waves. S waves, those are secondary, which are shear. Your P waves are primary, which are pressure. There are so many different subtypes, I'm not going to go into it. I mean, there's PKIKPs, there's SCSs, there's PCSs or PCPs. To put it in detail, this is the joy of a slinky. An S wave is what is called transverse. Okay, so this is transverse. Okay, would you think of the sine and the cosine? Okay, a pressure wave is longitudinal. I'm so sorry online, you guys can't see this. Wait, I don't have my thing on. A P wave, they go in a straight line, and it's literally going in line. Those are called longitudinal. Those are the two major types of waves. When they come together and they make a surface wave, that's where the destruction happens. And we'll get into earthquakes later. It's just sort of like precluding those. Your direction of the propagation of your wave, basically the wave's path, is what I just said in English, is controlled by density, it is controlled by temperature, and it is controlled by what is called the angle of incidence. How steep is the angle when it strikes something new? Incidence just means incoming. I said, I don't know how many of you have actually had physics?
I took college for this issue, but I dropped out because I didn't take
I took college instead of 15.
Well, I mean, it's like there's, if you took physics, you should know the difference between reflection, refraction, diffraction. You should know Snell's law. You should know incidence. You should know, those phrases should not be alien, but I know a lot of you don't. Oh, do physics, it's math. And so you go, oh, you do forensics, or you do something else. It sounds hard as physics, which I like physics. Physics makes sense. All right. I think there's like 6 things on here. 7, all right. All right, so the farther a wave has to go, the more friction it occurs within the earth, and the more absorption, which is called attenuation, occurs. So the longer the earthquake has to travel, the less destructive it would be at the very, very, very end. Just as a blanket statement. I mean, if it's a category, or not a category, if it's a magnitude 7 plus, it's still going to be destructive. But the farther that has to travel to get from point A to point B, the less destructive it's going to be. If the rock is more dense, it will travel faster. I don't know how well the history teachers have taught you like the weird facts, but American Indians used to dig pits in the ground, and they would stretch deer hides across it like a drum, like the top of a drum, and they could hear the buffalo running way before they knew that they were there, because it would make the drum beat. The beating of their hoofs as they were running across the plains made the drum beat. And they knew that they were coming. Have you ever seen the movie Stand By Me with the kids that have, I'm not trying to ruin the movie, but they find a dead body in the woods off the train tracks? I mean, I know I'm older than y'all, but it had a Joaquin Phoenix in it, and it had River Phoenix in it, and had a bunch of kids that ended up kind of had a. No, I'm getting old. My brain don't work anymore. Kiefer Sutherland was the almost said a bad word, was the turd older brother. But anyways, they're getting ready to go across train tracks that span a river. And before they go across the bridge, they stop and they put their hand on the rail and they listen to it because those sound waves travel faster through the rail than it does through air. Oh, really? Never seen that movie?
I think I did.
They do eventually after this. I'm not trying to ruin the movie, but it's a good movie.
Let's watch the next pro.
Oh. With temperature, if it's hotter, it will move slower. If it is colder, it will move faster. An S wave, a secondary wave, will not travel through a liquid. So when I heard, well, how do they know that the outer core is liquid? Because you get S wave shadows. P waves can go through it, but they bend. And so they make a different shadow. We've got seismographs all over this planet. In order to figure out where an earthquake comes from, we need 3 different stations to record, and we make a circle around them. Where those all intersect, that's your epicenter. Just like when they map you, like they always do, it takes 3 stations. They know exactly where you are. I don't care if you put it in airplane mode, y'all. They know exactly where you are.
VPN.
They can get around it, I guarantee you. I'm not trying to be all conspiracy theory, that kind of person, I'm not. There is no such, if you have a cell phone, there is no such thing as privacy. What?
Yeah, Facebook?
Yeah. Facebook?
Yeah, have you heard like, whatever you talk about, there's like ads.
Yeah, they track you like crazy. All you have to do is glance at something and it pops up in Facebook. Seriously. You don't have to buy anything. They track you like crazy. It's called marketing. It's called making money. All right, angle of incidence. Okay, what this means is when that wave hits something, how steep, like, was it 90 degrees? Was it 30 degrees? That's what incidence is incoming. How steep was that wave when it struck that mountain? Your layering, go back to superposition. That's going to control the direction of your motion. Don't worry, I'm not going to make you do any kind of geometry with this. Not this. When we get into earthquakes, I will expect you to be able to use a log rail. It's not hard. You just need to know how to use the equation. You need to be able to tell me if I have a magnitude 9.2 versus a magnitude 5.4, what's the difference in energy between the 2 waves? How many 5.4s is necessary to produce one 9.2? It's not hard.
Oh,
It's can you subtract?
yeah.
Can you use calculator?
Yeah.
Okay. The answer's Haley, stop eating in here and pull your mask up.
I'm not forced to be down back to Montana.
Right. D waves and S waves. Well, how do they know that the interior is solid and the exterior core is, or the outer is liquid? It has to do with the motion of an S or a P wave. I'm not going to go into this with depth. But we have seismographs all over our planet, and knowing where an earthquake occurs, where it starts, which is called a focus, we'll get to that when we do earthquakes. I want to say we do earthquakes on Friday. It might be Monday. I don't remember. Somewhere in the future. The way that it moves, transmissive, the way that it moves and it bends, and the way that it bounces off lets us know what is it traveling through. Is it traveling through a solid or a liquid? Is it traveling through something that is hotter or colder? And is it traveling through something that is more or less dense? And they literally make shadows. Now, I mean, not like what you think of as a shadow, but like a light, but like a sonar shadow inside the earth. Now, the one on the right, this guy, S waves don't travel through a liquid. So the mantle, even though it's fluid, it's still considered solid. But your outer core is liquid. So S waves, they can't go through that outer core. And so it has this huge shadow down on the bottom where you can't see an S wave. Whereas a P wave, not only can it go through a liquid, but when it goes through the interior core, which is not only hotter, but more dense because it's a solid, it bends it, it changes its speed. So where a P wave ends up on the other side, and where these shadows are, where no P wave occurs, lets us know specifically, understanding the diameter of Earth, how thick each layer is. Now, is it going to be like down to the millimeter? No. Like I said, the deeper we go in the Earth, the more attenuation, the more absorption occurs, the less specific numerically we have. But as a rule of thumb, we know that this layer is solid, this layer is liquid, this layer is solid, and it's approximately so thick. To answer the question from before the break, how do we know that? Seismographs. They measure earthquakes on what's called the Richter scale. There's actually 2 scales, but the Richter scale is probably the one that you've heard of. Richter scale goes up to 10. An earthquake that's at a magnitude of 10 destroys everything. It comes and like rip the earth in half kind of thing.
Wait, so S waves cannot travel through liquid?
No.
S waves cannot travel through a liquid. They can only travel through a solid. P waves, however, can travel through both. Which is why they had different shadows where you could not see that way, which is the previous one, which I don't think I put on your canvas.
But can S waves travel through both cores?
No, S waves can't go, they can go through the mantle and that's it. The exterior core, the outer core is liquid. It can't go past that. It's like it's deflected off the side. It cannot go through a liquid. We will have a section on earthquakes. Like I said, I don't put my thing out in front of me. Couple of earthquakes is the end of this week or the beginning of next week. I am building some documentaries into the lessons to break up the notes. Unfortunately, I have not been able to gather all of the materials that I wanted to be able to do to let you guys build stuff. Plus, stupid COVID, you're not supposed to touch stuff. I don't think there's one more. No, there's not. The next one's pictures. I don't know if you've ever seen, I know you've not seen one in person, but maybe like a documentary or I don't know, something on TV. It looks like a drum. A seismograph looks like a drum, and it's constantly spinning paper. And there's a needle that when you have an earthquake starts moving back and forth, sort of like a lie detector test, but it's not thoughts, it's seismic waves. This is what a seismograph looks like. And with this particular image down here, which I don't think I'm going to have you guys analyze these in depth, you really don't have anything but your P waves, which are the faster waves, are the first ones to arrive. And there is a time frame between a P wave and the first S wave. And knowing the differences between those, considering both waves travel at different speeds, that's how they know how far away from this particular machine that earthquake occurred. You get 2 more seismographs understanding this information, and that lets them pinpoint where that earthquake actually occurred. Isopachs. I will eventually teach you how to learn how to read a topographic map. When we did air pressure, we had lines where wherever they touched, whatever number was on there, it was the same number. It's the same thing with an isopach. but it's not pressure, it's height, it's elevation. There is a difference between going up and going down with the way that they are drawn on maps, but that's getting a little bit in that. An isopat just shows you the altitude of the crust of the earth. And I know y'all didn't study this over the break. Oceanic is thinner, anywhere between 8 to 10 kilometers thick. It is the more dense crust. It is the one that goes underneath. Continental crust is less dense, it will go on top. But it's anywhere up to about 80 kilometers thick. Now, 80 kilometers thick is right here, that is Mount Everest. Most of it's not that thick. Let's see, that's the Himalayas. This is the Andes, I want to say, which is Chile, over here on the left-hand side. Most continental crust is not that thick. It's your mountain ranges that are a lot thicker. But when they come in contact, and we'll go back over boundaries, because like I said, it's before the break. If you have an oceanic and a continental and they slam into each other, the oceanic, which is more dense, will go underneath. The continental, which is less dense, will go on top. Now, when they come in contact with each other, sometimes if this one's the continental, it's like it gets stuck and then all of a sudden it slips. And that's what causes tsunamis. And we'll get into all of that stuff when we talk about earthquakes. Tsunami is a Japanese word because Japan is where most of them occur. The worst tsunami that we had came from right here in 1965, and it almost took out Hawaii.
How are the squares in the ocean? Where like two waves combined and it creates like squares?
That is what's called a riptide. Okay, so if you go to the beach and you see what looks like you said, like a square kind of pattern, do not get in the water. That is a riptide. It's going to suck you out and drown you. It has to do with physics you've had. It has to do with constructive and destructive interference. So if a wave comes together and they're constructive, it is a much higher or lower at the crest of the trough. If it's destructive, it's flat. But when you have a riptide, the way that they combine with each other makes that weird like checkerboard kind of pattern, for lack of a better way to put it, and that means riptide. It's going to yank you out. Don't go in the water if you see that.
Like, does it suck you in there if you get in this?
If you get in the water and if there's a riptide that's occurring, it literally is pulling you out to sea. You can't swim against it. I grew up going to the beach at the Jersey Shore. I remember, I don't know, he was raised that way. When you see that, like I said, it's a checkerboard, big checkerboard, but don't go in there. All right, so the Mahoro discontinued, or the Moho for short, much easier to say it that way. The crust, what we walk on, there's this line in between it and the asthenosphere called the Moho for short. It is the boundary in between the two. I want to say that guy was Russian, because that sure looks like a Russian name to me. Named after the individual that figured it out. This is more of a refresher. I said it's been a while since we've done some of this. The mantle is the plastic, not like this. Not 100% solid, not 100% liquid, but that's more like a really, really slowly moving solid portion of the earth that has those convection currents that drives the plates. That conveyor belt, if you will, is called the asthenosphere. With the exception of the Moho, this is stuff that we covered a while ago. It's just been a little while. Our core. There are two parts of the core. The outer core is liquid. The inner core is solid. They're made up of the same stuff. The inner core is solid because it's under more pressure and it's hard. But it's still a solid because of the pressure.
But technically, by your glass.
Not the core. The core is a solid. The mantle, not the core, the mantle is like what I said with the glass. When I say like it takes with the convection currents in the mantle, it takes hundreds, if not thousands of years to be able to rise and fall. It's not like it's boiling water. Very, very, very slowly moving. And the few windows that I've actually seen that have shown as the glass settles and it bulges at the bottom, we're talking about like hundreds of years old glass. Like churches from the 1700s kind of glass.
Is that because they were already in the liquid and then heated up? So like,
It just had more time to settle.
so like concrete is a liquid.
No,
Oh. So glass is a liquid because it was already a liquid and then turned into a solid.
sort of, not really, but sort of. Glass moves, it just does it really slowly. It's hard to explain if you've never seen the type of windows that I'm talking about where it's very obvious that
No, I
the
get what
glass
you're
has
talking about.
settled. Because it's moving. It's just moving very slowly.
It's simple.
Yeah, I get it, but like, why is just glass like that? But why can't concrete or wood or plastic do it?
His glass is made out of,
Who knows?
sorry,
Glass is sand that's been struck by lightning. Yeah,
Yeah.
it is.
Have you ever seen a video of it? Oh, it is so cool.
yeah.
Just look up a video of sand into glass.
Sand, that's how they make glass. They take sand and they put it in a kiln and they heat it up. You ever seen how they make blown glass before? It's actually really cool.
I think, God, you said-
Yes, natural glass is
Like
when
the
lightning
old
strikes
natural
sand.
glass. I don't like it. Natural.
Okay. All right, so the Earth's magnetosphere is the motion of the liquid outer core as it's moving around, so friction, moving around the solid inner core, and that friction causes essentially a static buildup, which is what creates magnetic north and south. And y'all, our poles are wandering right now. They're moving at a very rapid rate, considering the rate that they normally move at. And we're worried that we're about to have another pole reversal.
If you were to slow down and speed up.
If it goes from a liquid to a solid, it is going increasing in density, which is a speed up. The more dense, the more solid, the faster a wave goes. As a rule of thumb. We did not go that far into the magnetosphere earlier this year. I ran out of time when we were doing the space unit at the beginning of the year. I could only fit so much in there. But this is what causes magnetic north and south. Now the flip. The Earth doesn't turn upside down. The poles flip. Where north becomes south, and it actually regenerates our magnetosphere, which is protects us from that hydrogen bomb in the sky that we lovingly call the sun. If it wasn't for the magnetosphere, y'all, we would fry. We'd be dead. There'd be no life on the surface of the planet. The only things that would still be alive would be the things that are within the depths of the ocean, where life keeps starting over and over and over again. I got one more. Okay, so like I said, Wegener just was before his time. He wasn't stupid. He just didn't have the technology. We have the ability now to analyze the silt, the rocks that are at the bottom of the ocean. And as we have the Mid-Atlantic Ridge, which is a split Pangea, that thing is breaking, making you slope to that seafloor, breaking, making you seafloor, and it's moving this way out from the ridge. Every approximately 500,000 years, we have a pole reversal, and it is reported at the bottom of the ocean, what is called magnetic striping, which is the really big nail in the coffin that proved plate tectonics. It's still technically a theory, but it happens. And we call that seafloor spreading, which we talked about before the break. I just didn't have enough time to go in depth to point to clients. Since we only had 2 sections. Before the break occurred. Now, hold on. I gotta check online attendance here real quick because I am missing people. I am missing people.
What you want?
Yes, go real quick. Okay, so I already got Avery. Did I get Billy? Yes, I got Billy, Braden, Camille, Christian. Okay, there's Jason. Marissa, Matthew. Okay, so I've gotten everybody else. Let me stop my recording. If you missed the 6 weeks